Welcome back to our computer feature extraction course in our edge detection segment. Now we're working on difference of Gaussians. It's an approximation of Laplacian and Gaussian operator and is used to dictate features that are blob, let me see, or edges, key points at different scales. It's calculated by subtracting one Gaussian smoothing version from the other smoothing version. Automatically here we know that there's a subtraction happening here. Effectively isolating features, be it edges or center of blobs at the chosen scale. This result is a multi-scale representing the image structure. So without wasting much of our time, we would see how we would carry out this difference of Gaussian by actually mind subtracting one version of Gaussians from the other. So welcome back. Here we are doing difference of Gaussians practically. The image we'll be using here, let's go ahead just as we've done in our presentation. Okay, so image, we're bringing our image. Let's load it in as CV2, CV2, ImRead, right? We've been able to bring it in. Okay, we need to convert it to a grayscale. To make that easy, we would cv2.cvt, then color. We've been able to bring this in. Then we say cv2 dot color underscore bgr to rpg, bgr to rb rgb, right? So we are cool to go. Good. We've been able to bring in our image and we're able to present it in a grayscale format. So now here we are looking at subtracting one gradient Gaussian smoothing version from another. So we are actually doing blur twice then. So just as we've done in our LOG. If you don't understand how this blur works, just try to see our LOG, which is Laplacians of Gaussian. You see how it works. Then we're doing the first one here. So cv2 dot Gaussian blur. So the first version we have is gray. Now I'm not using gray, I'm using sorry. So first image, then which is in grayscale format 5,5, which is our case size for the image. Next we look at the sigma, which is sigma x capital X. Here we are using 1.0 just as we've done in our original image, and here we are using for the second blur cv2 dot okay, Gaussian blur. We have Ife as an image 5,5, and we have our sigma value to be floating point. So we import the value, bring in the value sigma x, which is 2.0. So what do we have? Yeah. So we've been able to define a sigma value for a large blow and a smaller blow. So now we want to like subtract the two value to actually be able to get our difference of Gaussians, which is the major thing we actually have in here. So DoG, difference of Gaussians. So Gaussian is cv2 dot subtract. If you remember, in this image you are manipulating and you're in form of, you're in numerical form, so it is easy for mathematical operation to take place on them. 1 and log 2. So we're able to minus them now. So from here we'll convert our DOG to an absolute value. DOG of absolute value is cv2 dot convert scale to absolute value. So convert to absolute value, we're having DOG. So from here we have our result already. So let's see what is happening in our result. Let's peep. So plt dot in show let's see what's happening. Let's see. Oh, sorry, I noticed we made a mistake here. So it is not to RGB here, it is grayscale to gray. Yeah, because we're converting to a grayscale to be able to manipulate. Then we have so this is the result to be able to attain from this. Yeah, good. So here let's view out the outcome of our let's view the outcome. So the outcome plt dot figure, here we have fixed size let's say 12,6. Then we have plt subplot comma 4 1. Then we have plt dot in show. So we need the exact original image. We want to print the exact original image. This is the original image we have loading. This is how the original image we have looks like. So we need the exact original image. So we have to create the exact original image. How do we do that? We convert what we have to RGB. So image ife image in RGB, right? So we have it as CV2 CVT CVT. Then here from here now we have CV2 dot color underscore BGR2 to RGB. Right, great. So we've been able to do justice to get in the original image. So from here now we get the original image in to the spot plt.title. We have original plt.axis. I don't need axis for anything because I'm not doing any mathematical calculation, so it's fine. I can just remove it. So next I can just copy this and paste for my low sigma. The low sigma is first blur, then I give it the same p of gray. Okay, DoG as difference of Gaussian with sigma 1.0. So let us know the sigma we apply there, and that's the only thing. So here I'm making it 3. This is sigma 2. Here we use sigma 2.0 obviously. So the last version we are doing is plt dot subplot 1,4,4. So here we'll be having plt dot show the main difference, which is our dodge difference. So we'll paste it here. We have something like this. Down give it a title plt dot title dog, as difference of Gaussians. Then plt dot axis. Do we need axis? No, we can turn it off. So plt dot show. Finally, let's see what we have as a result. Yep, we've been able to get our result from here. And so just as I said earlier, our DOGs should have been white the way we have it in our normal background, but because of ID change, that's why we have this little difference. So thank you for joining us, and thank you for sticking with us to this moment. Next we'll be having determinant of Asians. Thank you.